Welcome everyone for this one of the spacetime seminar. It's a pleasure to have Dabholkar here, and he's going to tell us about edge.
Okay, thank you. Okay, it's great to be back here. All new faces, but it's some old faces. There are also some familiar faces, but the same room. It's good to be back. Okay, so this is work done in collaboration with and somebody who was here, Sandeep, student, who was then a postdoc at. So both Eleanor and Upamanyu. Upamanyu was a postdoc. Now he's at Amsterdam, and Eli is a postdoc currently. And I'm going to talk about, first of all, I will explain what are edge modes in quantum field theory, and then I will talk about edge modes in string theory and why it is interesting. So, if you take a path integral on some general manifold, so if you take a path integral on a manifold Y, let me call it M, which has this product form, then it has a natural interpretation in the Lorentzian Euclidean path integral on a Euclidean manifold, which is of the form S1 cross M, as a natural interpretation in Lorentzian as a trace. So, a path integral where phi can be a field with any spin, etc. I am writing it. You can interpret as trace e to the minus beta h operator on some Hilbert space. And there is a natural understanding, h is the generator of translation along the S1 because there is a translation invariance along that direction. M is where the wave function is the space-like slice, if you slice it, and the wave functions are defined as square integral functions on M, and beta is the length of the S1. Okay. Now, if you take a general there is no such thermal interpretation, right? We don't have. So, for example, if this was S1 cross S2, all this procedure will go through, but suppose we consider S3, then you cannot do this. But surprisingly, in a series, a very nice piece of work by Aminos, Denef, Law and Son, based on actually work of several people, which came from the, also partially motivated by higher spin theory and holography and ADS3 and so on. If you consider Y to be DS3, sorry, DS D plus 1 or Euclidean ADS D plus 1, merely thermal interpretation is possible.
Sorry to anticipate, but for the Euclidean ds d plus 1, we would say sd plus 1.
Yeah, exactly. And I took the example of S3 because, to be very concrete, Euclidean EDS3 is just S3. And it's clear on S3 there is no natural notion of slicing that you can think of, but in a way there is, because of it's such a symmetric manifold. So we know that in de Sitter 3, Lorentzian, so this is really, if you do the Euclidean continuation, it becomes an S3. And on this side is just a sphere, right, a 3-sphere. And you can imagine slicing it in certain way, which corresponds to So suppose everybody is familiar with the Penrose diagram of de Sitter. This is the static patch of de Sitter and a static observer going like that. This is one of the generators of the de Sitter group. So DS3 you can think of it as the, let's consider very concretely DS3, right? The DS3 symmetry you can think of it as SO1 comma 3 divided mod SO1 comma 2. Right, you can think of it as a coset space. S3 you can think of it as SO4 mod SO3, right? And what this means is that the isotropy group, which leaves the point fixed, which is the thing that acts on the tangent space, is SO3. Here it is SO1 comma 2, right? And the generator, let's call it L0. So you can sort of embed this in some Lorentzian space-time, putting one negative and so on. So if you have, so I think the L03, so you have a signature minus plus plus. So L03 is, you can identify with this generator. So, and we know that this, for this observer, she is in uniform accelerated motion with respect to, so it's like a Rindler observer, and she would notice temperature 1 upon 2 pi in the de Sitter radius units. So therefore it looks plausible that there should be a thermal interpretation.
I'm really sorry, but I'm somehow less familiar with the Euclidean ADS case being thought of as some kind of thermal. This is where it's...
So there you think of it as really ADS Rindler. So you use Rindler coordinates. Yeah, that's why in our paper we only talk about first about de Sitter. But Sun has written a series of papers where he has done it for ADS Rindler, where it has some of the subtleties that, I mean not subtleties, but it's a bit, it's not so immediately naturally obvious. But it's also not so unnatural in that, imagine that you have a Rindler observer in Minkowski space and you think of ADS as just some kind of a cutoff, IR cutoff. You're just putting yourself in a box. There is still a notion of a horizon for an accelerated observer. So there is a natural notion of anti-de Sitter Rindler's horizon, which is a generalization of the Minkowski-Rindler horizon. And the physics is quite similar. So suppose this is my partition function z hat. I put a hat because I'm slowly going to move to a worldsheet partition function. Hat refers to space-time partition function. Okay, this is a space-time partition function. Phi is taking values. This is a space-time field, and this is the space-time Hamiltonian. So the thing is that log z, and suppose you have a field phi I with some mass mi and some spin content si, which can be some representation of the relevant de Sitter group. Then question is that does this log zi have some thermal interpretation? And it turns out that actually it nearly does. And you can, these people showed that you can write it as bulk minus log z hat edge. Okay, whereas this z hat, another way if you want to write it as, it's like a ratio. Z hat can be written as z bulk divided by z edge.
So this z hat now is a partition function on the
So yeah, let me explain all the terms. So this is just a partition function. For example, if you take a scalar field or on a S3, you can just sit down and calculate. It's not complicated, right? Because the Laplacian on S3 is just basically you can express everything in terms of y LMs, and you know the eigenvalues and you know the multiplicities. So you can write down the path integral more or less by inspection, right? Then you can try to do what is z hat. So z, this is well defined. This you define as trace e to the minus 2 pi h. This. And what you find is that something is left over. It doesn't exactly equal. And what is left over is you can call as the edge modes. Now, why do we call it the edge modes? I will come to that.
Because each hat in this context would have a continuous spectrum, right?
Uh,
The way you defined it. It's like the modular Hamiltonian of one.
yes. We will come to that point. It's a very important point because if you try to go down that track and diagonalize the Hamiltonian, you will come to grief. And that's.
For scalar, one also gets this edge.
So for scalar, these edge modes are absent. Very good observation. But for higher spin, they are present.
So just to ask, sorry, so if you actually did it for the metric, I don't remember the story in DS3, but in general, you know, it's all just the bulk path integral is almost a partition function.
Correct.
Except for some prefactor,
Yes.
you know, which is I to some power.
Exactly. That's
So
the
that
Z
I to
edge.
some power is this.
Yeah.
Oh, I see.
No, not just some phase. Some really, no, it's not just a phase.
But I mean, you know, because there's been this whole confusion about that prefactor, but now Maldacena and so on have interpreted it by saying if you introduce an observer, the world line of the observer, then, you know, very beautifully, up to a sign, everything cancels. And
I see.
yeah, there's some story. Okay, anyway. That's
So is this also related to this paper of Longo, Witten and
I see.
De Sitter in with an observer? But I think,
Yeah,
no.
They were trying to interpret the work of Pennington.
Pennington, Longo.
But in a path integral formulation.
Okay.
And so they said, well, what Witten et al. Found was a good interpretation of the entropy if you introduce an observer.
Okay.
There are all these subtleties with the Euclidean path integral, but let's introduce an observer.
Ha.
And they found, you know, things.
Then
that
agreement
seem-
with this
so-
algebraic quantum
Yeah,
field theory
Or
picture.
at least so that it became an exact partition function with the prefactors. Okay, but that's a aside from.
So I should look at it. There could be a relation. But here the point is that this is a completely well-defined quantity you can calculate. This is this is at present not a completely well-defined quantity. So what they showed was
Sorry, Atish, maybe here's the question, but can any number not be written as a trace over e to the minus 2 pi h for some h? Some operator h?
no, not some operator, like this particular operator. Meaning it really has a thermal meaning. So let me explain, right? So why do you expect an edge mode, right? The main problem here is that your this slicing breaks down at the bifurcate horizon, right? There is a point where the space-like slicing is breaking down, and there is an analogous breakdown on the Euclidean side, and so you are sort of choosing a slicing which has a problem at the bifurcate. I mean, and as you know, all the interesting physics of black hole physics and holography, everything really comes from this point. So that really point is a very important point. And things are stuck there. So that's the heuristic reason why you expect something over there. So it's not, so I will now give you more precisely. This is not just, of course, you can write any number as sum of two numbers. And the important point is that they gave a very nice and complete formula for any mass and any spin in terms of the Harish-Chandra characters of the
So just to ask, you could do this in flat space also, right? Just take.
so you could do, but these formulas are not known, the Harish-Chandra characters for the inhomogeneous Lorentz group, which Poincare group are not, I mean, I'm sure something like that, but since these ready-made formulas are available, it's useful to first understand them. So Harish-Chandra characters of the de Sitter group, which in this case would be, I will just say the de Sitter group in general SO1 comma D.
So Atish, this trace is to be thought of as a trace over the Hilbert space on the hemisphere?
So here it would be the trace. So that's the question. So how do we define the trace? Okay. So that's where the Harish-Chandra characters comes in. As you know, Harish-Chandra is a very famous Indian mathematician, and who became famous basically to understand the representation theory of non-compact groups. So he started with Wigner's representation theory, which actually I remember, Sandeep, you had as your VSRP project.
That's right.
I mean, it's a beautiful paper of the little group and the representation theory of Poincaré group all you are familiar with. But then I think then Dirac tried to think about de Sitter group, which is a SO1 of 3 or 4 or 5 or something like that, and that's SL2. So I think that's how our Harish-Chandra got into this field. And so, I mean, don't be scared by this. It's not some. The main thing is that what is a character, right? A character is like trace of, like, for example, you can calculate the character of SU2. Character of SU2, you can say y to the power j3, or if you like, e to the minus 2 pi x to the j3. So this is like mu, which is y to the power j3, right? And you can calculate it in a given representation. So it will be something like, I don't know, 1 minus y to the power j plus 1 or something like that, 1 minus y, right? So it's just a trace in a finite dimensional Hilbert space of some operator. Right? That's called a character. But of course, you know that non-compact groups have irreducible unitary representation. Are infinite dimensional. So there are all kinds of subtleties, because if you take trace 1 is well defined in a finite dimensional thing, but it's not well defined in a. So which operators are trace class? I mean, for which operators can you define a trace? How do you define the trace? What measure do you use? Things like that. There are all these kinds of subtleties which were resolved by Harish-Chandra. And because the group theory is very powerful here, because you have such a nice symmetric group, these characters are completely known. And these characters are calculated in a certain way and not by diagonalizing the Hamiltonian. And if you diagonalize the Hamiltonian, you actually don't get sensible answers. So basically, if you do things correctly, mathematically correctly, you get some answers. And you can write this log z basically. So let's look at log z, okay? So log z, right, you would write it for a field. So it's basically you have, I wrote down this d phi, it will be something like e to the minus phi, some operator phi, right? You're doing one loop calculation. So you're going to get a determinant, and then you're going to get a log of the determinant. And log of the determinant, you'll write it as trace, log det is equal to trace log. And then that log, you will use the Schwinger parameter representation, and you will write it as dt upon 2t trace e to the minus that operator.
Sir, if I'm interested in partition function on the Euclidean sphere, why at all should I think about 1, d? So 1, d.
No. So there are two things, right? Here, you will only think in terms of SO4. No, some of these steps, we are so used to doing it, and we do it intuitively, and we forget actually they are quite non-trivial, even in flat space, right? You start out by writing a path integral on, let's say, R4, right? Let's take an example of R3 versus R1, 2. This is the analog of S3 versus DS1, 2. Right? What do you do? In R3, suppose you had a path integral, you just do the path integral. And what will you do? You will write it as dp e to the minus t p square dt over t. That will be the log determinant calculation, right? Because and p square, because you're in 3 dimensions. So these are the kinds of things you will get, right? You're summing over states. But you can interpret that because when you quantize a field in Lorentzian space, you will get a Hilbert space which is a unitary representation, which is infinite dimensional, and particle representation, and you can interpret that as a trace over those states, which we sort of just take it for granted and we do it. We want to just do that process carefully.
I was wondering if the fact that you are kind of forced to think about a hemisphere, I mean, because you are thinking about the hemisphere, that you are forced to think about.
No. I'm thinking, so this calculation is as simple as the R3 calculation. I will do it as honestly as you would do an R3. I'm not doing any hemisphere or anything. I'm just calculating the Euclidean thing. Question is, I want to have a Lorentzian interpretation. What will I do with the Euclidean answer unless I can interpret it with?
So, I mean, for example, the determinant of box is well defined up to say 0
Yeah, up to 0
on
metric.
the sphere.
On the sphere.
That's the meaning of his log z. But then he's going to try and break it down.
Yeah, so in fact actually maybe
Sorry, just to be clear, this trace is not the same as that trace, right? This was like a wall line kind of trace.
sorry, exactly. I was about to correct myself. Is exactly you're right. So I have to use, let's call it trace word line. Okay, because then I'm going to use another trace, the world sheet trace. Okay, so it is. In fact, as you said, you can basically, how would you have done it in flat space, right? You would have done it as e to the minus t m square, e to the minus t p square, sum over p, because the Hamiltonian is diagonalized. That would be in flat space. Same thing you can do here. The m square gets replaced by nu square, which is a more natural thing for AD sitter, and this sum over momenta gets replaced by this quantity. But I will explain what this is. This is the analog of p square. Basically n plus 1 square. I am talking about de Sitter 3 now, just to be concrete. So you have a Laplacian on S3. The Laplacian eigenvalues of Laplacian on S2, for example, it would have been LL plus 1 and 2L plus 1. Right. So if you were computing a scalar field trace, you would just write it as e to the minus t LL plus 1 or 2L plus 1 sum over L. That would be the trace that you would calculate. So you do the same thing with this, as you are saying. All these are just group theoretic quantities, dimension of the representation, and the Casimir, quadratic Casimir relevant for the Laplacian.
Then what is nu square then?
And nu square I will write down. Nu square is basically m square, but it has this correction coming from if the particle has spin. Okay, so this part is clear, right? There is no hemisphere or nothing. I'm just taking the Hamiltonian, which is the Laplacian. I'm taking the degeneracy. So I diagonalize it and I do the degeneracies for that particular quadratic Casimir. It's like the angular momentum. L labels the representation. I will consider a massive. Good point. It's a subtle point. Let's see. Let me see if I can remember it.
No, but for a massive field, you don't have to worry. I think, right? I mean, there is no zero.
No, but the box will have a zero mode. It's not. Just the Laplacian will have a zero mode. You're right. But I think it's not subtracted. No, I think you can include it. But it doesn't lead to a divergence because what you're saying is that it doesn't lead to a divergence.
Then it's box plus m square.
Yeah, so meaning that, so the zero mode is included here, and you don't have to exclude it because even if it is included, the t integral doesn't diverge because it's damped by the modes. No, but there are subtleties with the zero modes of ghosts when you do the Fourier-Popper quantization. That's why the sum goes from -1. But this is very nicely explained in quite detail in these papers. But so there is some non-trivial calculations that go into this result, and you can look at it in the paper. And
just sorry to keep interrupting, but just to connect to the earlier comment about Maldaceno's recent, for the graviton especially, because of the conformal factor.
Correct.
There's a real issue, right? Because the path integral in Euclidean signature is not positive. So you have to rotate the conformal factor and choose a contour and then try to define things. That's how the whole story of the prefactor.
So even for the Euclidean path integral, you're saying,
Yeah.
because of the conformal factor, there is a.
There is an issue of how to make sense of the path integral because the the quadratic fluctuation analog of box is actually not bounded below once the conformal mode is included. So like in string theory, we rotate.
Like the Polchinski's thing, the x0 mode, which is the conformal factor if you think of it as Liouville, basically. And you pick up some I.
Pick up i's in front. And
Correct.
Story.
Yeah, then there is a story.
I remember it being related to the fact that the geodesics are kind of unstable, right?
And then that's right.
Yeah.
And
if
so
you have a geodesic at the equator, it can slide and.
that's right.
So then an unstable.
So then the story is you include an observer, then you get extra slippage modes, and they cancel the i's. It's quite a nice story. But anyway, I'm just saying, it might be fun to think about that.
Meaning I would like to understand it because where does this show up? Because this is slightly a representation. So graviton in 3 dimensions maybe, see the thing is that I actually, so when we did this work, we chose DS3, the formulas are known in higher DS, but DS3 somehow avoids these subtleties because graviton is not a propagating mode in 3 dimensions.
Could very well. Okay.
So
it might be interesting.
No. So I'm not saying this is not interesting. As you will see, I wanted to simplify the calculation to upgrade it to string theory. So we took DS3, which is the simplest case. DS3 has many advantages. That a lot of the things are not propagating, and also all the group theories kind of the little group is SO2, which is abelian. So which simplifies a lot of. So the representations are all one-dimensional. Okay, so this part is clear, right? This is the Euclidean part.
This is just this is the character, right? The character.
This is not a character. This is just a Euclidean calculation. Right? There is no character here. There is no infinite dimensional representation, right? This is just everything is finite dimensional. This is the Euclidean calculation. Sorry, this.
We are not talking about the Harish-Chandra character.
Not yet. Okay. So point is that this is the Euclidean calculation. Everything is finite dimensional. We are talking about SO4 representation theory. Right? But now we want to reinterpret that as an SO1, 3 representation theory. And that is given by these people, and you can write this as du by u. I will not explain, but the steps are not complicated, okay? I mean, if you can more or less follow. If you had more time, I can even explain this. It's some transform of the characters. And you can always write it in this form, where the chi u is trace in the global Hilbert space of e to the minus I u h, where h was this generator L over L0. So this character is defined, a particular trace defined by Harish-Chandra. And I can actually going to write down a very explicit answer, so don't worry about it. Answer is it actually not, it's not difficult. I just want to say that it's not difficult to derive it, okay? So it's not somebody's magic or something. If you just follow a little bit of, see, I mean, remember, just to simplify you, right? If you look at L0, L1 and L minus 1, the Virasoro group, they already generate the de Sitter group SO1, 2, right? It's a rotation of SO3. And if you were doing some representation theory, what do you get? You know, you typically get this kinds of, this raising lowering operators gives you this. Typically when you do partition functions, you get 1 minus q to the power, and it to the power n, to the power 24 and so on, right? But here we don't get it to the power n, you just get some, because don't have this L minus n's. So okay, so it's very plausible. What I'm saying is that, think of this as like it's like a Virasoro character would have had this going to the power n.
But you have some notion of a lowest weight state and all that.
No, this is not a,
it's not like that.
no, this is a principal series, okay?
So this is in principal series. There, how does it go?
No, so for a principal series, you cannot, I mean, the principal series is a bit more complicated than what, this, but okay, I'm just trying to simplify. Yeah. Just I want to make it familiar to you. It's not, so these kinds of factors are not surprising when you do characters. And this you can think of it is like the, yeah. So this is it's like a sum of two terms. And this character is like the kind of formula that you typically encounter when you calculate characters.
But because it's not a highest weight representation, action by these off-diagonal elements would take you up as well as down, right?
Yeah.
So that wouldn't that give rise to a divergence mainly?
No. So that's the, you can define it properly so that it actually doesn't have any problem. And the edge, this is bulk. And edge is also very similar, which is some other, so this is some prefactor, okay? Just this, without this factor. Okay, so what I want to say is that it's a completely explicit formula. And now I want to bring your attention, this is missing this piece, this bottom piece. And it has to do with the fact that you are living in two lower dimensions. So in general, this will be a representation of SO 1 comma D, and this is codimension 2, oh sorry, behind the horizon. So it's SO 1 comma D, and this is a character of SO 1 comma D minus 2. Sorry, no, D minus 1. Something is wrong. Sorry, this is of D plus 1, and this is D minus 1. In our notation, D is equal to 2. So I'm thinking about DS 1 comma D. Right? So DS 3 is really DS 1 comma 2, and this is a representation of SO 1 comma 3, and this is a representation of SO 1 comma 1. So it's really a very simple representation. It doesn't have this factor.
And Atish, DS2 is, or DS whatever, is just a...
Is some prefactor which I will write down now. So this is 2, but there is a more general formula for general D. In this case, it's just 2, because SO2, it's a representation theory of SO2, and you only have 2 helicities, so it's 2. Otherwise, you'll get some additional factor. And this is a little bit more complicated, which is important. DS minus 1. This is S plus 1 whole square. Sorry, this is S square. Okay? So when, as you were saying, if you have a scalar field, this term is absent.
I should think of as some parameter along the world line?
No, U is not exactly that. It's some, you do some Hubbard-Stratonovich trick and so on. It's not, I don't think it's related to T. It's not related to the world sheet, world line. It's just some parameter when you process it.
Atish, can you explain what the G is? Trace over what exactly is this?
Global de Sitter patch. So you might say that how come the global thing is related to the static patch? But because of the Bogoliubov transformation, there is a one-to-one map between the global Hilbert space and so that's why actually the two traces are actually turn out to be equal.
And where is the edge in the geometry?
So so first of all,
the natural thing would be hemisphere, so that you have a boundary, and that's where these guys will live.
no. So this is in the Lorentzian picture, right? And this is codimension 2, evidently. And where is the codimension 2 surface? The codimension 2 surface is here at the bifurcate horizon. So the edge modes are all localized at the bifurcate horizon, and they only see the transverse direction.
But that codimension 2 surface is a totally Euclidean guy, right?
That codimension 2 surface is totally Euclidean.
So then how come it has a comma in that? So 1 comma D plus 1 D.
No, this is the character of SO1 comma 1.
Yeah.
So therefore, you are in 2 dimensions less.
It's roughly intuitively, it's as if, the bulk thing is a slice in bulk, but propagating in time, and the edge thing is just localized at that
point.
bifurcation point, but propagating.
Propagating in time. And since your transverse direction is only one dimensional in this case, it's a one dimensional transverse directions propagating in time.
I mean, roughly, is it?
Roughly, correct, that's correct. But in fact that even might be actually precise.
But within time meaning along the horizon.
No. Here, right? So you are saying that, see, when you interpreted Lorentzian, right, you have to take a space-like slice.
Yeah.
And that is propagating in time. So here you choose a space-like slice which is d plus 1 dimensional propagating in time. So that's why SO1 comma d plus 2. And then you drop in dimensions and you, yeah.
But SO1 comma 1 is like a stabilizer of the horizon, right?
Correct.
So this is the chiral modes. The chiral modes on the horizon.
Yeah, I don't think we should try to make direct relationship. So what I'm saying is that this is a mathematical fact that this calculation gives you this, which you can process and show that it is equal to this. It has an interpretation as a character of de Sitter group, one in the de Sitter group of your interest, and that you would have stopped there if there were no edge modes. But there is actually leftover piece, and the leftover piece is also surprisingly given by another de Sitter character, but de Sitter character of codimension 2, of 2 dimensions less. And this is just a mathematical equality.
Atish, sorry to refer to some of Manu's and so on and so forth, but if you think of gauge theories and you think of entanglement, then you have to define the entanglement carefully, and you again get an edge mode contribution. Right?
So your paper has been prominently cited in our
Sorry, it's a poor taste, but
simply because Upamanyu, I was telling Upamanyu, no, we don't need to cite this paper. No, so your paper with Soni and Ghosh and also with Soni and Moitra.
And that's not the reason.
No, but I will, what you say is a very important point, has to do with the physical interpretation of the edge modes, and they exactly appear to be, in the case of gauge field, they basically come from the fact that you have to impose a Gauss law, and the Gauss law relates outside degrees of freedom with the inside degrees of freedom, because some, like if you think in terms of link variables, right, some condition has to be satisfied. So the inside variables are not exactly independent of the outside variables, and that's the reason for the edge modes. And this is quite nicely analyzed by several papers like Wall and various people, Donnelly. But then this gives a natural generalization also to massive fields, where you have to use some Stuckelberg fields in a Fierce-Pauli system, where the interpretation is a little bit, it's not obvious how to relate it to the Gauss law constraint, but it's related clearly to gauge invariance. So exactly, so edge modes are very interesting because they apparently have something to do with a broken or unbroken gauge invariance, and if you have massive fields, is basically broken gauge invariance. And in case of string theory, there is apparently some infinite broken gauge invariance because you have infinite number of, and so if you are able to do the edge modes for the string thing, it's actually telling you something about the gauge symmetry of string theory. So that's why it is an interesting thing, but also because of its connection to entanglement entropy. That was partially my motivation.
So how are you saying that these gauge modes lives on bifurcation point and bulk mode lives on the space?
No, I mean, so that interpretation I will withhold for now, but it's clear that this is a character of de Sitter group 2 dimensions less, and this is a character of a de Sitter group of the entire space, right? And it's heuristically not unreasonable because all the breakdown of the slicing is happening at the, so if anything, the select preferred point in this diagram where things are breaking down, otherwise you would have had a thermal interpretation, right? Far away you should have a thermal interpretation because there is a natural slicing. So thermal interpretation is breaking down only at this point. So it is natural that the edge modes are to be identified as being localized there. But
so even in that case, I mean, if I just for simplicity ignore those points, then the thermal interpretation is for the space which is half of the full circle, right? In the
you are thinking that how if I do the Euclidean continuation.
So I'm half, which is what is being moved up and down by this generator, right? So should I not identify these states on half of the sphere rather than full?
You know, in this, if you take that global slice and you think of that as being generated by some Hartle-Hawking wave function, right, then the calculation of the S3 partition function is a natural thing from the point of view of
The global slide, the global coordinates.
the global coordinates.
No, but we also want to have a thermal interpretation, right? And that seems to be only changing one side. In Euclidean case, it would, if you have just not, I mean, even one less dimension, S2, you would just have this angular phi that is going around, right? And it's this arc that is being taken around. So it seems that the natural Hilbert space, which might admit the thermal interpretation, is the one on half space. And then naturally it has also edges, and then there will be that edge there.
Although, okay, let's come back to this question because I want to finish something.
Yeah.
But at this level, it's just an equality, right? I mean, I'm not even, let's not even try to interpret it, right? That there is an interpretation of this Euclidean formula in terms of this, which has an interpretation in terms of a trace, and the other piece which does not have an interpretation in terms of trace. And it is necessary to add that piece for reasons which are purely group theoretic, which has a physical interpretation in some cases like a gauge field because of the Gauss law constraint that you have to impose. Okay, now let me talk about edge modes in string theory. Okay. So now imagine you take bosonic string theory, compactified on R1 comma 2 cross, not compactified on T23 or S1 to the power 23. So I will take this S1 to be of radius R. Right, and what will happen if I take bosonic string theory? I will get a whole set of fields and states in R1 comma 2, but I can now replace this by ds1 comma 2 and with very low curvature. So basically, like we are living in de Sitter, but we don't even know that we are living in de Sitter. So you expect that the near horizon physics is not affected by this, and this is just a kind of an infrared cutoff. And because somebody has worked out these formulas for you, I want to go there rather than derive these formulas in ISO 1 comma 2, but that could be an interesting exercise to do actually. So you can think of this.
Just to understand your notation, so R12 is the plane in 1 and 2 directions?
Yeah.
And then S12 is the circle made out of 2 and 3?
Yeah, 23. So there are 23 circles. This is, yeah, you have a 26 dimensional bosonic string.
Okay.
This 23 is not labels, is actually number 23.
Okay. Got it.
So you have 23 circles and you land in a 3-dimensional flat space, and the 3-dimensional flat space you replace by de Sitter. And fortunately, these people have done all the work and they have given you this explicit formula which is valid for any spin and any mass.
This is for open string?
This I'm going to do closed string theory. So now let me see why I am interested in this.
This is a solution of string theory.
It's not a solution of string theory. It's a good question, and you can actually do it with ADS3 cross S3, which will be a solution of string theory. But once again, I'm interested in taking a very large R limit, large radius limit. So the length of this is L and the radius of this is R. So I'm going to take infinite L limit in the end. And we actually run into some remnant of this fact that the equations of motion are not satisfied. But I'm going to ignore that point for now and focus on only the edge modes. So you expect that the edge modes will not be affected, because even if you take the radius to be very large, they might be affected in a very mild way. And we are also trying to do the calculation in ADS where this question doesn't arise. Because you can put an S3 and then you ensure that the equations of motion are satisfied. Because this will be like an NS situation. NS fiber and NF in bosonic string.
And the tachyon of bosonic string won't come back to
It will come back. I mean, it is there in the story, but that is so we are. I mean, sort of we are doing the superstring on the side where this problem is not there, but the presentation is much more complicated. So we decided to go ahead and publish this because, but it is all doable. I mean, hopefully. I mean, there are issues like this. What you're saying. Okay. So the idea is the following. That suppose I am given a log zi labeled by, which gives the label by the species, then I am going to think of string theory as like a string field theory, okay? Not, I mean, not in this scary version of Ashok, no, that it's just a simple collection of modes, okay, at one loop, right? You are not doing interaction. So what I mean by string field theory is that, okay, just list all the fields and you regard them as normal fields and you sum over them, right? And those fields are labeled by I, and if I sum over them, I should get this string theory version of this partition function. And as you know very well, the logarithm of the spacetime partition function, so this would be the logarithm of the string field theory partition function at one loop, but this is known to be the spacetime partition function of the worldsheet partition function of the string theory. Right? You know how this happens, right? Is everybody familiar with that idea? But basically, you know, this is a summing over a loop, this kind of, it's a loop, one loop diagram, right? But if you have an exponential of the loop, one loop diagram, it's going to give you one loop diagram, I mean, disconnected diagrams, right? With some factorials. So if you take the logarithm, you'll only get this single loop. And that's, you fatten it up and it becomes a string one loop diagram. Because you're summing over all the modes, you can fatten it up.
So actually, I'm already confused about something here, which is that in open string theory, I totally agree with what you just said. But in closed string theory, if you just take the point of view that you're going to sum over all the particle content to one loop calculation, you seem to get like you don't seem to get this cutoff in modular space on the joints.
Correct.
Is that right?
That is correct. That is correct.
And I'm confused why.
No. So therefore, what you do is, so this was a calculation done by Polchinski for so thermal thing, and the cosmological constant piece has this. I mean, see, you are absolutely right that the fundamental difference between string theory and is the modular invariance. And if you have a modular invariant answer, then you can think of restricting it to the keyhole region, and that is central to the ultraviolet finiteness of string theory. So modular invariance will not be guaranteed if you just take a generic list of particles. You will not get a modular invariant answer. So therefore, string theory does more than, this is not, you are absolutely right, so I should probably put a question mark here a little bit, or it's an approximation. And you will have to there restrict the modular integral by hand.
Okay, so that's just put in by hand.
That's going to be put in by hand. But you can put it in by hand if the resulting answer is modular invariant. And it is not guaranteed a priori if you just did a sum like this. And that what we will discover is that for the edge modes actually you get quite a non-trivial and nice modular invariant answer.
No, but Atish, correct me, but I think Polchinski showed more, right? That is, if you summed over all windings in the particle picture.
So Polchinski showed that for the thermal part, you actually did, this somehow happened automatically.
It happened automatically.
But for the non-thermal part, which is the cosmological constant, you have to do it by hand.
Okay.
Yeah.
But the thermal part.
Thermal part, basically the divergence got reinterpreted as winding modes along the time direction. Okay, so basically, where am I? I'm a bit lost. Okay, so let's now do therefore this and sum over it. So if you do this, it's actually what I was calling, I will call it tau 2. What I was calling t becomes tau 2 now, because I'm preparing for the, so I'm going to write tau is equal to tau 1 plus I tau 2. And you have something like sum over n plus 1 whole square e to the minus pi L square. This is the string length, which I will just drop now. L square. So everything is in string units. And this nu I contains the information about the mass and the spin, because nu I depends both on the mass and the spin. And here the spin representation theory is simple, because otherwise in higher dimensions the representation would be some symmetric tensor of a higher group and so on. Here is just it's one dimensional representation, so just the helicities plus or minus of a given state. So that's why it's actually quite a simple quantity. And now you take the large L limit.
Yes, so I understand this is written first in de Sitter.
Yeah, this is all in de Sitter. And now I'm going to take large L limit, because I really am interested in the large L limit. I'm not.
But sorry, I missed something. Excuse me. How do we know the de Sitter spectrum in the string case?
No. So in the large L limit, I expect that the string spectrum is going to be the same
as flat space.
As flat space, because in the large L limit, it's not like suddenly, if you had a trillion light years of a de Sitter horizon.
But L is the de Sitter radius.
Is the de Sitter
So
radius.
if you are using the flat space spectrum, shouldn't it have been alpha prime or something? We know.
No. So alpha prime is here, sitting here, L square. No. So I will explain. Right? Think of it as some kind of an IR cutoff. Right? You are putting it on IR cutoff. You are putting it in some long IR cutoff. And now I want to take L to go to infinity. Right? So what is going to happen, right? I will write n plus 1 is going from -1 to infinity. So actually write n plus 1 divided by L to be P, like a momentum, right? And then delta P is equal to like 1 upon L.
So that's how you get the zero mode part.
So you'll get L cube, you'll get L cube d tau 2 divided by, you can do now the tau 2 integral. You'll get P square and P square here. So it will be the standard momentum integral in flat space, not surprisingly. And you will get up something like tau 2 to the 5 by 2. And then you are left with e to the minus pi L square tau 2 mi square. In the large L limit. Okay. And then you can repeat. So now you just have to sum over mi's in flat space, and this is the calculation that so you can now, I'm just first doing the bulk calculation just to remind you what Polchinski did. So you'll get something like L cube from this integral. Then you can introduce the circles and sum over them, and mi is going to contain also, it's like also the Kaluza-Klein momentum, because we are thinking of it as a 3-dimensional mass and not as a 26-dimensional mass. So basically the condition is going to be L square mi square divided by 2 is going to be n plus n tilde, these are the minus 2, plus 1 upon 2 r square sum over n r square L square, r going from 1 to 23. These are just the Kaluza-Klein momenta. Okay, and then what you are going to do, convert the Kaluza-Klein momenta also into momentum integral in the large R limit. So I am basically going to take limit r going to infinity and L going to infinity. These are just some IR cutoffs, and so I expect the answer to go as L cube r to the 23 in string unit, so like L to the power 26, d2 tau, because you introduce the d tau 1 integral to impose the constraint that n is equal to n tilde, as we normally do. So your integral becomes d2 tau with just a single power of tau 2, but you will get all this tau 2 to the 3/2, and then you will get, so basically you will get tau 2 to the power 13 coming from the 26 dimensions. So this becomes tau 2 to the power 14, and then you will get the trace over, this is now a world sheet trace, q to the power n minus 1, q bar to the power n tilde minus 1. No, like you would have done, like Polchinski did, where he used toroidal IR cutoff. Here I am using de Sitter cutoff, but it should not matter in the large R limit.
And just so I make sure I understand everything, the gamma I square there is basically mi square with some spin dependence?
Sorry?
The new I square in that formula, sorry, the previous.
Which nu I square is mi square plus s square, but the s square term is subdominant in the large L limit, so you can actually approximate it to this order. Okay, so where was I? So now this trace I want to do, but this trace can be done because you have 24 transverse directions in the light cone gauge, etc., the usual story. So you basically will get up a formula which is d2 tau upon tau 2 square. This is the Weil-Petersen measure, which is modular invariant, and you will get some cosmological constant density. And the cosmological constant density is just eta to the 24 tau absolute value square divided by tau 2 to the 12. And this tau 2 to the 12 is the leftover from this, right? And now you see this is modular invariant, this is modular invariant. Here it was over a strip, as you were correctly saying, but now I will by hand restrict it to, and then this formula has the tachyonic IR divergence, but it is free of UV divergences. Now the formula that I wrote down for edge modes also has UV divergences. So this is the fundamental question that we have been trying to understand, that entanglement entropy in string theory should be UV finite, which is what I have been, and all the physics there comes from again that point. And one way to get to that is to use this orbifolds method and to do analytic continuation, which is what I had been pursuing, and that is sufficient to show, actually we were able to show that the resulting answer, if you can, the analytic continuation is free of UV and IR divergences, but we were not able to get a modular invariant answer, I mean despite trying. Witten was able to do this analytic continuation for open string answers and was also able to show that it is free of the divergences which seem, so they disappear in the correct physical regime. But that calculation was also incomplete because open string is not really complete theory, you have to include closed strings, and for closed strings, even though we were able to show finiteness, we were not able to show modular invariance. So we were looking at part of the entanglement entropy answer, which is the edge modes like you encounter in theories with gauge symmetry, which also have in quantum field theory they have UV divergence. And the question is that can this UV divergent quantity in quantum field theory become UV finite in string theory? Because then that would be an indication that string theory is sort of the type 1 algebra in some sense. From
Are you saying that what you were trying to do earlier by including these orbifolds, etc., has more than the edge modes you will talk about here?
Yeah, I would have thought so, because as we know there is a hot thermal bath and there is a contribution of the thermal bath which also gives a contribution to the UV divergent term. So right now I don't want to speculate about the precise relation between the two, but I would say that it is a priori the two quantities are independent.
Yeah, I mean just to say, to the extent that in the gauge theory this is due to these edge modes are due to Gauss law constraints.
There is clearly an additional thing that is present also for a free scalar field.
Yeah,
right?
Or for physical photons.
For photons. So therefore you expect that the edge mode is not the whole contribution. Yeah.
So I mean, as far as this question of finiteness of entanglement entropy, etc., is concerned, wouldn't the leading order piece be important also? The sphere, the one that.
Yeah, if you are interested in the entanglement entropy, it's absolutely important, and that was the goal of this stringy replica method that we were developing. That using that method, if you actually succeed in getting a proper analytic continuation, as Witten was able to do for open string, if you actually got so we were able to do analytic continuation of of the divergent pieces, and we had to mangle we were not able to find a explicit modular invariant analytically continued answer.
No, but I was talking about the sphere, not even the torus, the leading order part.
So the leading order part in my paper I showed that you actually get the area term out of analytic continuation.
But wouldn't that zeroth order calculation in string theory be just computation of sphere partition function?
Yes, and you might say that it is 0.
Yeah, I mean,
Right.
so
But it turns out that this folklore about the sphere partition function being the space-time action is not true when you have boundary terms. So if you have a Gibbons-Hawking boundary term, it is not captured by the sphere partition function. So it's an open question how to reproduce the Gibbons-Hawking boundary term from a world sheet calculation. So in my paper, I use a kind of a world sheet reasoning to find the one loop partition function. And it contains more than just the sphere partition function. There is a boundary term which is very important. Okay, sorry. Okay. So I have now 5 minutes. Okay.
No, of course you might want to.
Okay, let's take 15 minutes. I think in 15 minutes I can do that. Can I take some water?
Of course. You want some tea?
Or maybe something more substantial.
Coffee.
Coffee is good, and water is.
You're lucky that Shiraz is not here, otherwise there's no chance we would have ended before 1:40.
That's right. Okay, now if you look at the edge modes, so now you look at the character for the edge modes, right? And character for the edge modes was compared to this had an S square term. So now you have to do a sum over Si square e to the power okay. So how you now go through the same steps that we went before, but now SI, what is SI? Is the spin of the field, the spin of the state actually. It's not the spin of the field, it's the spin of the state, because you are summing over states. And the only states in 1 plus 1, I mean in 1 plus 2 dimensions, they are all labeled by the little group of a massive state. So the only non-propagating massless state is a photon, but a photon is dual to a scalar field, so it doesn't have any edge modes, and all other massless fields are non-propagating, higher spin. So you only need to deal with massive states with spin, for whom the little group is SO2, and they are labeled by helicity, +1, -1, +2, -2, +3, -3 with arbitrary masses. So you just have to sum over those things. But what is the helicity? The helicity is just you can represent the helicity in terms of the oscillators of the world sheet, right? Because if you, for example, right, if you had a state like alpha -1i, alpha -1j acting on the vacuum, this will have a helicity. If this I and j are the directions 1 and 2, it will have a helicity in the 1-2 plane, right? And so basically you need the spin operator in the 1-2 plane, and you need to calculate the trace now of this quantity. So you end up calculating a trace of the spin operator square, but s plus s tilde whole thing has to be taken together, times q to the power n minus 1 and q tilde to the power q bar to the power n tilde minus 1. So how will you do this trace? As you know, it's always better to exponentiate this. So you write it as e to the 2 pi mu s plus s tilde, and then you take two derivatives. And this trace can be done in terms of theta functions and eta functions, right? Because it's just oscillators with theta functions and eta functions. And the answer is the following. So it's basically limit mu going to 0, this chemical potential going to 0, del square by del mu square, some partition function in this 1-2 plane and its complex conjugate as function of mu. And this is actually given by sine pi I mu eta tau divided by theta function. Okay, so I can sort of rationalize this for you. I mean, basically you have one complex boson, right? So you expect to get something like product of 1 minus q to the n square, but because you are putting a spin, it will have some e to the pi I mu, 2 pi I mu. So you have x and x bar complex boson. So this one, the oscillators of this will give you plus and the oscillators of the other one give you minus. And then you multiply by 1 minus q to the n and divide. So that gives you this eta. And you don't have the zero modes because you are actually just summing over spins and not over. So it's easy to see that this formula will follow. And if you do this expansion, what you get, so you get an answer for the.
So this is one complex boson per the circle.
No, just you are in DS12, so only one complex boson in the plane in which you are. The circles are not complex. The circles are just gone.
When you do it in string theory, you will include your KK modes.
You will include all the KK modes, yes, when you do the trace. Yes. But they don't carry spin. So the trace is restricted to only one complex boson. Trace over spins is restricted to one complex boson.
Just to confirm, but the calculation is so far just like in the flat space, right?
Yeah.
The de-Sitter-ness has entered.
Has not entered, yes. And the answer that you get is L now, R to the 23. So you see the 2 powers of L have dropped. So it's really codimension 2. d2 tau over tau 2 square, lambda tau, and tau 2 e2 tau plus tau 2 bar, tau 2 e2 tau bar. Okay, this is what you get. Where e2 tau is a quasi-modular form, it's known as a quasi-modular form, or it's the second Eisenstein series. But I just want to write to you, it's like a derivative of the eta function, or the 24th power of the eta function.
I should have asked this question in your previous section, but maybe was it correct that in the previous, when you were doing this bulk sum, you were getting power of 26 there, like L cube times R?
Yeah, we were getting L cube R to the power 23, L to the power 26. It has to be dimensionless, right?
I find that a little bit confusing because to the extent that we are calculating an entanglement entropy.
No, there we are computing just the cosmological constant in 26 dimensions.
That was the bulk, so to say.
So the bulk piece is lives in 26 dimensional, and let me write it more. Right, you just take eta function. You see, you remember eta function was something like that. 24 powers is something like that. So if you take the logarithm, you will get sum over this, and when you take derivatives, this 24 will come in front, and you will get a nice sum. Sum over n. Okay. So it's a very explicit function. And moreover, it has a very nice Q expansion. So that's very nice because it suggests that maybe these entanglement modes have an interpretation in terms of some worldsheet calculation.
So Q is e to the 2 pi
I tau.
I tau. And it's the same lambda tau, right, as you got in the bulk.
Yeah. But actually there is a constant term, okay, which we ignore, okay, and that constant term we believe has to do with the fact that the de Sitter is not satisfying the equations of motion. So in addition to this, we get a constant term.
But where is the de Sitter?
No, what I'm saying is that de Sitter does not satisfy equations of motion. So you expect some indication of that to show up, because so there is a constant term which we don't know how to interpret. So we are actually going to drop it. I mean, I will come back to that in the end.
And that constant term will break modular invariant.
And you can make it modular invariant, but it seems to lead to a divergence, which we don't understand. But we expect that when you do it ADS3 cross S3, that constant term will be absent, because of the way DS3 and ADS3 and S3 will come with opposite sign and cancel it, but we have not checked this yet. Okay, but E2 tau is also, it's called quasi-modular, because you can combine, you can write E2 hat tau, which is E2 tau minus, so this is holomorphic, right, is holomorphic in tau, but it is not modular. But you can write this as minus 3 pi tau 2. This is not holomorphic now, because tau 2 is the imaginary part of tau, is tau minus tau bar. So this depends both on tau and tau bar. But now this transforms as a modular form of weight 2. So that means E2 tau, like E2 minus 1 upon tau, will be tau to, or let me write it, A tau plus B, C tau plus D. So basically you can write this in terms of E2 hat, and you will be left with, so basically you can write this answer can be written as tau 2 E2 hat tau plus E2 hat tau bar plus 6 pi. Okay. This actually just renormalizes the cosmological constant, so this is not important, this also you can drop. It's like a subleading correction to the cosmological constant, which is modular invariant, so we can drop it. But this is not modular invariant as it stands, right? This has nice modular properties. But we know that this can be mapped to this by elements of the SL to Z group which belong to gamma infinity, right. These are basically elements of SL to Z which leave basically translations. Your gamma infinity is the group of translations like tau into tau plus 1. It's of the form 1n 0 1. Okay, and you sum over all the n's, and which leaves the infinity fixed. So this is the gamma infinity. So you consider elements of gamma modulo this group. But basically all that it means is that instead of having A, B, C, D, you're basically doing a transformation, and then tau 2 goes to tau 2 plus C tau plus D. And the elements of this coset are labeled by C and D, because the elements of gamma are labeled by A, B, C, D, subject to AD minus BC is equal to 1. So there are only 3 integers, and using this gamma infinity you can get rid of one more integer, and you can label every element by C and D in 1-to-1 correspondence. Okay, so therefore you can write this as the final answer as F tau E2 tau plus F bar tau E2 bar tau bar.
Just do the modular completion by hand.
Yeah, so it looks like we're doing the modular completion, but this actually, what is F tau? No, and then we will map it into the keyhole region, and then the question is that is this modular invariant? If it is modular invariant, then you are done. But it's not obvious that it is modular invariant. In fact, F tau is actually 1/2 tau 2 okay.
I'm so very sorry, but just F tau was what? I'm so very
So I'm just defining. So what I'm saying is that we went from this strip to this, and every time we this this strip has infinite copies inside this, and every time we map each of them, it's related to by some C tau plus D. So basically, you end up summing over all C tau plus D, right? So F of tau is just summing over all CDs. And that is of the tau 2 is like, okay, and this has, as I told you, this has weight 2. So if you want to get modular invariance, this should have weight -2, right? And actually it does, because tau 2 divided by C tau plus D whole square is kind of modular invariant, summed over CD, but this is not, and this picks up a -2 weight. So a priori it looks like you're done, but this sum is not convergent, because you see you're summing over CD, and it's not, so you are not actually done. So how do we now make sense of this? But normal thing that you do is to do analytic continuation, like the famous -1/12 of Ramanujan. But I mean, you should have some modular invariant regularization, right? And a nice modular invariant regularization is to just multiply this. So instead of this, I consider F tau S.
So Atish, in the ordinary case, when this kind of you go from a strip to the keyhole region, it is the same problem where that summand is 1, right, essentially, and then that also in infinity, which you know, the kind of question that Onkar had asked.
For cosmological constant?
Yeah.
Exactly.
Very similar thing.
Yeah. But there the final answer was actually modular invariant. No, here this is more like this winding mode story, meaning here what is like there what happened was that you could unfold, you go from this region to that region, and then the actual answer became equal to this is what is happening here, that you are getting some additional modes, which in that case were winding modes along the time direction, which were not present in the field theory description. And then the answers were, you didn't have to then by hand restrict yourself. So this is a bit different from the cosmological constant, where you had to restrict yourself by hand. If I get this function to be nice and modular, then the restriction has automatically happened.
If it were nice and modular, you say, oh, string theory is so clever, it converges.
No, but it's better than the cosmological constant. It's more like the thermal piece, where right, in the thermal piece what happened was that you didn't have to restrict by hand.
Yeah.
So because the thermal piece actually doesn't have a UV divergence, right? So what happens is that you reinterpret the field theory answer as some over also winding modes, but now restricted to this region. And that's the analogy here, and not the cosmological constant.
So you have an interpretation.
I mean, I don't have the interpretation, but I mean that is how it is working out, and not like how it works out for the cosmological constant, where you have to restrict the domain by hand.
One way to say that is in the cosmological constant you introduce a space-time temperature, right, as a regulation.
No, but even if you do that, there is a temperature independent piece, and that you cannot get rid of.
Okay.
So you cannot regulate that piece away,
I see.
and that piece you have to do this by hand. Whereas,
In a sense, what you have said is that, okay, the full thing is contributing, but I'm going to restrict to keyhole and images. This
no,
is the
and
image.
so but that's exactly what we did in the thermal case, that you start with this and where there are no winding modes because in the original field theory answer, and then you map it to the keyhole region, but in the mapping you introduce an additional integer, and that integer you interpret as the winding mode. So you are actually writing this answer is equal to that answer, and then you don't do anything, you don't restrict anything. That's the kind of thing that seems to be happening here, okay? But unfortunately this is not modular, this is not convergent, but you can do this very easily by introducing this factor, and it's not actually very, this is very natural, because see tau 2 is like the Schwinger parameter, and this is like dimensional regularization, right? If you did dimensional regularization, P integrals, if you do, for every dimension you get factors of tau 2. So this is like a modular invariant dimensional regularization, right? You are introducing some additional, you are going to take S going to infinity, you are going to go slightly away from, it's going slightly away from 26 dimensions, because that would seem to break modular invariance, but you do it in this fashion, which is explicitly modular invariant, okay? So if you do that, this can be actually written as minus 2i tau 2 square del by del tau bar 1 upon s e tau s, where e tau s is known as the non-holomorphic Eisenstein series. And which has modular weight 0. And non-holomorphic Eisenstein series is simply 1/2 is basically a modular average of tau 2. And this is actually a very popular object in number theory and so on. You can think of it as a modular average of tau 2 to the power s. That's the non-holomorphic one. And this operator is called mass lowering form, lowering operator. So what is happening is that this object has modular weight 0, and the mass lowering operator is like a lowering operator, and it lowers the weight by minus 2. So starting with an object of weight 0, you get an object of weight minus 2. So if you can make sense of this object by analytic controlling in S and take the limit S going to 0, you are done. And it turns out that this, so we thought that this is again a complicated thing, but it turns out this is some famous formula in number theory known as the Kronecker limit theorem, done in 1863. So we didn't have to do any work. So it's really clearly an important, it's there also in textbooks now. It's like Lang's algebra, you will find Kronecker limit formula. And basically using Kronecker limit formula, you can show that this, because of some, like the Riemann zeta function has some properties, this function also has some symmetry properties. So instead of considering S going to 0 limit, you can relate it to S going to 1 limit, because it is actually kind of symmetric between S going to 1 minus S. And basically it turns out to be related to this quantity. So E tau S, Kronecker tells us, has this behavior. I mean, this also can be derived, it's not something very complicated to derive. Plus a constant plus terms of order S minus 1. The important thing is that this coefficient could have depend on tau, but it doesn't. Okay? And since our function is actually a derivative acting on that function, this divergent piece as S goes to 1 actually drops out of the picture. So it's really like very nicely drops out. And you are left with just the derivative of this in the limit S going to 1. So the final answer looks like the edge mode partition function is LR to the power 23 divided at L24 E2 hat tau. And it turns out that this actually the derivative, if you remember, derivative of the eta function was E2 tau. So actually this turns out to be also related to E2 tau. And the final answer is something like that, E2 tau bar. And this has weight 2 comma 0. This has weight 0 comma 2, holomorphic and anti-holomorphic. And this has weight minus 2, minus 2. So this whole thing is modular invariant. So you end up getting for the edge modes a nice modular invariant answer, and now the integral is automatically restricted to the keyhole region. And this admits a Q expansion, so it looks very likely that, so it's basically giving you information about the infinite power of gauge, broken gauge symmetry modes of string theory in a very nice modular invariant compact form. And it would be very interesting to figure out if you can get it from world sheet and expanding. What do you? I mean, I think there is probably a lot of information contained there, which was worth looking.
How did you get that form of towers? Is it like comparing with that?
No, this. So this is the famous Kronecker limit formula. No, it's a calculation that you cannot. No. So you have to take. So this is a non-trivial result. It's a highly non-trivial result, meaning you have to first of all do this analytic continuation. The analytic continuation is given in terms of some Bessel function, etc., etc., etc. It's all known, okay, and the steps are easy to follow. It's not very highfalutin mathematics. You can kind of, it's really very practical. You can actually sit down and do it in an afternoon. And the non-trivial thing is that analytic continuation has this limit formula, that it has this behavior. This is 1863. So since this result existed, we didn't have to do any work. Otherwise, you would have to figure out how to make sense of this by analytic continuation. Okay, so therefore, I think it's an interesting and it is ultraviolet finite, so at least the edge modes lead to ultraviolet finiteness in string theory and modular invariance, and what they imply is something to be explored. Thank you.
I'm really sorry, just to make sure I got the chain of logic fully right. So you began by, say, doing a scalar field, and you had the, say, the Euclidean partition function, which you wrote as a sum of two terms.
Yeah,
right?
yeah.
And then when we did string theory, we had a similar Euclidean calculation.
No, so I'm just thinking of string theory as a infinite number of field theory modes.
Infinite number?
And for each field theory mode, which will have some mass and some spin, this 4-author paper, Aninos, Denef, Law and Son, have given us a formula. So therefore, just like we could do the sum for Polchinski, so you could try to do the sum for them. A priori is not obvious because you have to sum not only over mass but some particular combination of spins that appears. But luckily the spin combination that appears is quadratic in spins, and it turns out to be related, you can do a simple derivatives of some theta functions.
No, I understand.
Yeah.
So that was the edge mode calculation.
Yeah.
And then there was the whatever, the bulk or whatever from which you were subtracting the edge mode. And does the bulk also have some, and then there was this lambda tau, right? Now just to make sure, the lambda tau was the bulk contribution from which you were subtracting the edge modes to get the full answer, or?
No, lambda tau was the bulk contribution.
Was the bulk contribution. No, and the left hand side, the full Euclidean was the
bulk contribution minus this. Yeah.
Okay.
Now the thing is that the bulk contribution also has some subleading terms which we have not analyzed, and they will also have the UV divergence, and I think the entanglement entropy will depend on a combination of both of them. So that's an interesting question which we have not addressed, but it's one can try to analyze it using these methods. But we first wanted to do the superstring and the ADS3 and then address the bulk contribution.
And presumably the bulk contribution has this volume dot divergence which will drop out when you look at the...
Because the volume divergence will give you the volume cosmological constant, which you ignore.
Well, I think if you have a way of
If you have a superstring, then it will drop out, otherwise it will be there at one loop, right?
No, I think if there is a way of calculating the
Then the entropy formula it will not contribute.
Yeah.
So you're right that these people talk about relating it to entropy by doing some derivative with respect to L.
Exactly.
If you do derivative with respect to L, then that term will not
I
contribute.
think it will
But I didn't want to go there because there are all these issues about whether you'll introduce a conical singularity, when you change the temperature and so on. So but I think what I'm saying is that all these questions are addressable.
Sure.
I mean, in this way of doing things.
Maybe I will just to make sure. What I was thinking was, if you take that bulk term, maybe you already answered this. Can you massage it similarly to get an answer which corresponds to the scalar contribution or the heat bath contribution? That is the non-entanglement part.
So that's
That's what you're discussing.
sorry, no, non-entanglement part is just the cosmological constant.
But it should, so it should care about a contribution coming
From the heat bath,
horizon.
from the heat bath.
area.
But the heat bath you expect to be the subleading 1 upon L square contribution, which I did not calculate.
Okay, so that's what you meant.
Yeah.
And
Entanglement can't have a volume level.
it can't have,
It only
okay,
have an
yeah.
area.
But is it hard to, I mean. that-
No, it's not hard. I mean, we have not looked into it. No, because it's not entirely clear to me yet. I mean, there are issues about whether you have to introduce a conical singularity or not, right? But it's a very natural question to ask and natural question to answer. But we just said that let's first focus on the edge modes, right? I mean, the title of our paper is edge modes. So we didn't want to pollute it with partial contribution coming from the bulk modes.
There, since it's entirely localized, it seems like it's entirely coming from the edge. You don't have to worry about taking derivatives.
Exactly. The point is that for the edge modes, the separation has already happened and you don't have to take any derivatives.
So why for the bulk do you have to do temperature? That might be one way to compute it.
But another way to,
regulate, I mean.
yeah, you can just look at the 1 upon L square term.
I mean, your philosophy.
Yeah, you could also look at just the 1 upon L square
yeah,
term
and regulate.
and think of that as a, so subleading term which is down by 1 upon L square, you could try to identify with this, and this is certainly something that we are, I mean, it's a natural question to ask, and we are, I mean, it's worth looking at and we are looking at
I
it.
mean, a posteriori, if the answers are sensible, you may say, oh, my regulator is a good one. You
Yeah, I agree.
But I think it's slightly subtle as you're alluding to, because you want to change the temperature, right? And
To compute the entropy. So it's not partition function but the entropy. If you want to compute the entropy, you will have to take the derivative of the partition, the free energy.
You're not exactly in the 3 sphere anymore. You're introducing a small conical deficit at the bifurcation point. So it's like you have to move away from the sphere.
But these people try to argue that you could just vary L. So I didn't want to get into that conversation. Yeah.
No, sorry, I mean, I think I missed it. So this connection between this part, the string 3 part, and the previous part where you talked about this decision and this character and this, so that I missed.
That character, if you look at that character, the edge character, it ends up being, and reprocess it, it ends up being just computing trace S square.
Okay.
Rather than computing trace 1,
Okay.
q to the n minus n naught.
Okay, and then, but the calculation here was done in flat space only, right? Not quite.
And calculation is done in flat space. I mean, otherwise I don't know the spectrum. I mean, I'll have to
So just
resolve the Virasoro.
This is just doing this edge modes in flat space, right?
Is you doing edge modes in flat space?
Using the formula that was.
Exactly. So if as Sandeep is saying, there should be some kind of Wigner-Inunu contraction of the de Sitter group to Poincare group,
Okay.
and then the character should contract to the characters.
Right.
But as you know, I mean, sometimes the SO1 comma groups are simpler than ISO.
Just to say, in de Sitter,
Yeah.
actually the relation between entropy and Z is clearer.
Tell me.
See, because what happens in de Sitter, there is no.
Free energy is not there. So yeah.
So the entire Z, is.
So this is what these people say, that the Z is equal to that. So maybe I should just do it. Yeah. I mean, I was just.
How can that be right? There's a volume law divergence.
No, what I'm saying.
Huh.
If you take, if you literally could do the de Sitter case with the infrared cutoff in place, right?
Okay.
At finite L.
But the question is, I think that argument is true in that you're saying that it's like, the question is that what part of it is the entanglement entropy? Because as he's saying, there is a volume divergence.
See, if you take a de Sitter
Mhm.
and you sort of break it in two,
Mhm.
right? Because there is no, it's a closed surface and there's no energy.
Yeah.
The whole contribution is entropy. Okay. Now, what entropy is?
That's the
Entropy
question.
is it's the entanglement between the two edges.
Or it could also be the entropy of
Two
the,
static patches.
yeah.
There's nothing else, in de
But
Sitter.
it could scale like volume.
Well, I mean, you have some finite radius de Sitter, and the area of the bifurcate horizon is in units of.
Yeah, but
de
the point is
Sitter.
that if you do this calculation, you will get a L cube term also. So it's not, I mean, what I'm saying is that you would discard as saying it's a cosmological constant and it's not really entropy. That's how it looks like. So you could say that entropy has a cosmological constant term,
Yeah.
which is not to be
That's right.
right, because that's the energy, vacuum energy.
That's it, and that's exactly what happens when you do the field theory limit. See,
Correct.
when you do the field theory,
You will get the h bar omegas which were present also in flat space,
that's right.
and that is not somehow to be taken into account or something like
That's
that.
right. That's right. So let me just summarize the field. Sorry, but
No, so tell me. I'm interested. Yes.
Take root gr, right?
Right.
Minus lambda. And
Right.
you do the field theory path integral, right? First, you have a saddle point contribution, which turns out to be the radius of the area of the S2. Then you have a one loop determinant. Right?
Correct.
Now, that one loop determinant, of course, diverges, but because of Wilson, up to the conformal factor, those divergences can be interpreted as renormalization of the cosmological constant and G Newton.
Okay.
I'm doing this in just root gr gravity. So you
Okay.
So now you say, okay, but those go into the renormalization, and
What is left?
is literally the area with a one loop correction. So it's
Okay.
very suggestive that it's
I agree.
Now it's the area. What is it? It's got to be the entanglement entropy. of the
Correct.
loop.
Okay, that's
Correct.
Or you just declare it to be the entanglement.
Yeah. So I think here my feeling is that it will come out quite nicely because we have already isolated a term which looks like the cosmological constant. So you throw that out.
Yeah, yeah.
You don't keep it in, right? What is not clear is that what part of this is renormalization of Newton's constant. But that's why we wanted to do superstring first.
Yeah, that's
Because so that's our step is that we are doing first the superstring theory. But you're right. I mean, I think it's not edge mode entropy partition function is not very from the entanglement entropy that we are interested in, and then it would be very interesting if you can get the same. I mean, that will also give you something to shoot for from the replica method that we were trying to push. So that should be the final answer from the analytic continuation.
The only thing is because de Sitter is not a real solution.
Yeah, but I think that problem also we feel that is not difficult to resolve because you just take anti-de Sitter across S3, which is a solution, and you take the large L limit.
There is the only thing is this argument that the partition function is entropy in anti-de Sitter because you have a boundary energy. It gets more tricky.
Exactly. So all these issues are there. Yes.
So there are some things which are simpler in de Sitter.
So that's why we decided. Yeah, we were otherwise we thought that if you try to solve all these problems in one paper, it will be too much. But I think it's already quite non-trivial that you get something very nicely modular. It's not just something modular. You get really something which looks very physically, possibly interpretable.
So if you expand this and see what the low energy.
Yeah, that's exactly. It should be because what is expected is that for a particle of a field of spin S, there are from the analysis of the partition function in quantum field theory, it looks like there are S square degrees of freedom, field degrees of freedom stuck on the horizon. So that's why you are getting codimension 2 contribution multiplied by S square. So that analysis we can do easily now with the Q expansion and see whether it matches up or not.
And then you can also possibly do this Donnelly-Wald type analysis to see.
So the thing is that Donnelly-Wald analysis has not been extended to Proca fields.
About
See,
this-
because for a Proca field, there is no Gauss law constraint, naively. But, or there is no gauge invariance in a way. I mean, you can write it in a non-gauge invariant way, right? But actually the correct way to do it is to do it as a Stuckelberg mechanism, and you introduce a gauge invariance, and then you gauge fix it. So,
in string theory, there is already a gauge invariance, right, in the form of the BRST operator.
yeah. So for string, I mean, the point is that if you have a Proca field, right, you have something like minus the square 4 plus mu n. This is not, this is a massive theory, but it's not gauge invariant. But the Fierce-Pauli method is that you write this as dB minus mu whole square. I mean, del mu d, and introduce this as a, so this is like a del mu b is like an axion field. And now this is gauge invariant. If you take b going to b plus epsilon, and mu goes to mu plus del mu epsilon, this combination is gauge invariant. So now you have a Lagrangian which is manifestly gauge invariant. Now you do the whole thing, you gauge fix, you introduce ghost field, Fourier-Popov, etc., etc. And now you can calculate everything in a manifestly. And, but there is no Gauss law constraint in the, I mean, so the sum of this thinking, I don't know, so the Donnelly work kind of, I'm not able to.
The Donnelly one was just, sorry to put it
Yeah.
like this, but computing what for a gauge field would be the contribution from the boundary mode.
That's right, yeah. And they have a classical, they just look at the classical phase space, and they ask if you write down the symplectic structure of the theory on some subregion, or maybe this is Donnelly and Friedel,
Well, one of them is.
yeah, on some subregion, and they ask what kinds of modes do you get on the boundary just by looking at the symplectic structure. And I think you could possibly do that as string theory.
Okay, or you can just.
But my question is that what happens for a massive field? They can do it.
Okay, I mean,
I
I
mean-
was thinking that you, sorry, I was thinking that you would just look at the BRST operator, which is like the analog of the gauge transformation, and calculate from that.
So when Prabhu was talking about, isn't it true that all the gauge invariances sit in some other ghost number?
Yeah.
So there is one physical ghost number that we have a physical set of states, and then for the other ghost number we have, say, all the ghosts.
Exactly.
So your thinking is that
Exactly.
this might be matching with that
Yeah.
spectrum of ghosts.
Yeah,
But you have, so what is the story with Donnelly work for Proca field?
you know, I would have thought, now, you see, because, okay, you can do it in that way, but you can
That's
just
right.
do it, no, sure, but you can just do it ab initio.
You can just do it ab initio.
Yeah, in the gauge theory discussion, this corresponds to what's called the electric center,
Yes.
way of doing it. And you just set up the calculation saying, okay, you have the Gauss law constraint, how much entanglement does it lead to?
No, but my question is that so electric center comes about because Gauss law relates the outside fields to the inside fields.
Yes, okay.
So, right, so when you think, I mean, suppose you have a lattice cutoff, then it's really a bipartite system, naively.
Correct.
And you would have thought that the inside and outside commute with each
Correct,
other.
correct.
And there is nothing in between that relates the two. But the electric center is the kind of the piece which is not exactly commuting, because you're relating the inside links to the outside links, right?
That's
But
right.
my question is that there is no Gauss law when you have a Proca field.
But you have, there's, if I take the A0 equation, you have something like divergence of E is equal to some, I'll have to think, something involving dB here, right?
Yeah.
D0B,
Yeah.
some momentum.
Yeah.
So, you know, at that vertex on the boundary where links meet, right? The gauge degrees of freedom, A mu
I
degrees
see.
and B degrees of freedom are not independent
Not
of each other.
independent.
The total flux coming in is something like the conjugate momentum of B. I have to think about it, but
Yeah, so I try to follow sort of the literature trail in this, and somehow Donnelly and Ball and various other people seem to have gotten stuck at the Proca field.
I said you couldn't do it. So maybe there's a, but Terupamani.
But this kind of thinking would
No,
tell you
earlier
how
also we discussed this and we couldn't find a clear paper where the Proca field has been discussed in a similar manner.
Okay.
So whereas in this other way of doing it, I mean, I don't have to try to, I mean, it would be very nice to connect it to the constraint because that's the physical picture. But here you are sort of doing a calculation, right? You are doing a trace and you are saying it's equal to, so you're doing a path integral and you say that it doesn't equal a trace, it misses something.
Maybe the phase space way, of course, seems the most sophisticated, should work, but I'm just saying there's an in principle brute force. This system can be put on the lattice, you know.
But you expect that this will also have a center.
I mean, there's one constraint at least for sure. You know, it's
Because it's not a propagating degree of freedom. You say that
Yeah.
it's a Lagrange multiplier.
Yeah, because you know the point is that if you want to set A0 equal to 0,
Okay.
you're going to get a constraint, right? Now, whether it leads to entanglement or not, I don't know, but you can just set up the problem.
I think it would be very nice, I mean, I looked at it, yeah, it's a very good problem.
Where is this Jyotirmoy guy? He's always doing this kind of his runoff. Some grad student, let's
Who always
we can
does
do
this.
this. No, Jyotirmoy is thinking of it. Yeah, we can set it up.
So I mean, my thing is based on sort of incomplete information, I would say. Meaning I've just done a preliminary search in this thing. I also talked to people like Wong, who was at Cambridge, who was working on it. And I didn't somehow get a feeling that they have understood the proper field. The same level of detail as they have understood.
But the structure of gauge symmetries in string theory is very complicated, right? In the sense
And also
that you
string theory
have
is very
ghosts and then the
complicated.
ghosts of ghosts and ghosts of ghosts and so on. So this might work for some low-lying fields, but
Right.
if you want to actually get that formula out, then maybe some systematic, this
And
BLST way of
that's why
doing
we
it.
went down the Harish-Chandra character way, because there the explicit formulas are known, without interpreting in terms of Gauss laws. Because there it's just a mathematical equality. Path integral is equal to
No,
trace
but in
plus
string field theory, you can understand the Hilbert space also.
probably. I completely agree.
But so how are you suggesting that?
It's complicated, but it just comes out of BRST operator.
Yeah,
I come out of BRST operator, but okay, maybe there's a way to phrase the entanglement.
Well, no, I was not thinking of the entanglement, but just looking at the gauge fields, right? The ghost fields. I mean, I'm thinking that this is somehow counting that, right? The gauge degrees of freedom. The physical degrees of freedom.
I could at least never do the entanglement calculations introducing the ghost, because the ghosts are these negative norm, crazy things, and then you have to define entangle. You know, roughly you might say you have some entanglement for the gauge theory and then some for the ghosts, and they cancel and all that. But the ghost might be it's well understood.
he's not talking about space-time ghosts, he's talking about these worldsheet ghosts.
World sheet ghosts.
So,
Is that what
worldsheet
you're
ghosts
talking?
are-
BC.
No, I was talking about the space
Space-time
time.
ghosts? Okay.
Yeah, that's what I
I was
thought.
thinking like in the BRST operator there are worldsheet
No,
ghosts.
those are worldsheet ghosts, right? When you talk about ghosts, I mean,
No, but there was
string field theory, those are worldsheet ghosts.
But he said ghosts and ghosts for
Yeah,
ghosts
yeah,
and
yeah.
so on. So I
that
thought
kind of
he
a
meant,
complicated structure appears for the space-time,
For
and-
space-time.
but that comes out of worldsheet BRST
You
operator.
are saying that for closed string.
Yeah. Worldsheet BRST operator. So the entire tower of gauge degrees of freedom
Yeah.
comes out.
Yeah.
So I don't quite know what exactly this is being counted by these edge modes, but I was thinking that maybe those gauge symmetries, these unphysical modes are being counted.
So there is some part of this character can be understood as, see for example here, if you do this,
Yeah.
the gauge fixing is something like the Fourier-Papa ghosts are just like M C bar C or something like that. So you can say that the Fourier-Papa ghosts have zero modes. But the B field doesn't have zero modes because only its derivative appears. So there is a mismatch between, so when you, normally what happens is the determinant, bosonic determinant cancels with the fermionic determinant. But here what happens is the zero modes of the C field don't cancel. And they actually are left over and they make a contribution to this, but they are not the whole contribution. They make a contribution to this edge character, to make it into a character. So there is a, the ghosts clearly play a role if you do the quantization properly, but I don't think they account for everything.
You had done a calculation in, was it in open string field theory?
Yeah, but not the edge mode. Like edge mode, what we did was we basically looked at Witten's string field theory, and we wrote down the phase space of Witten's string field theory, and we looked at like what contribution do you get at the boundary. And you get some contribution in terms of the BRST operator and so on. There's some expression. And then we took the limit where the Witten string field theory approaches Chern-Simons theory. This is the same one. And there we were able to consistently show that it agrees with the Chern-Simons answers. Yeah, but I mean, I would not be able to explain this formula, for instance, or some other.
Yeah, I think it is kind of a bit of a miracle that these people have an explicit formula for all spins in terms of characters. I mean, very explicit in terms of Harish-Chandra character. I didn't. I mean, because of that, we could do this calculation.
Yeah.
Somebody had done the work for all states. And if you try to do analysis along the lines of Kronecker, I think you get stuck pretty quickly.
Yeah.
Right? Imagine trying to do it for a random tensor field with a random. I mean, I'm sure I think it's a good question to see how to reproduce these formulas of these 4 author paper just at the field theory level.
Correct.
For a random speed. Arbitrary. Great food.